4.7 is on inverse trig functions. Now let's just remember a little bit about what it means for a function to have an inverse. For a function to have an inverse, it must be 1 to 1. That means for each x, there's only one y value, and for each y, there's only one x value. That's 1 to 1. 1x for every y, and vice versa. So, y equals x is 1 to 1. For each x, there's only one y. For each y, there's only one x. Now, the famous vertical line test is often invoked to determine whether or not a function is 1 to 1. So you can see at no point does any vertical line hit the graph of y equals x more than once. Now if we consider y equals x squared, this is no longer the case. Here's y equals x squared, and you can see that the horizontal line test, it fails. Y equals x squared can have two x's for one y, right? So like y can equal -2. You can have, hold on. Here, this could be -2 comma 1, and this could be 2 comma 1. All right, so for one y, you have two x's. All right, so it's not 1 to 1, OTO. Okay, however, oops, I don't want to do that. If the domain of y equals x squared is restricted, see right here, y equals x squared, the domain is all reals, right? It can go to positive infinity or to negative infinity. X is all reals, okay? But if you restrict the domain to x is greater than or equal to 0, then, so in effect you're removing this part of the graph, okay? So now, then y equals x squared, domain x is greater than or equal to 0 is 1 to 1, or y equals x squared is 1 to 1 if the domain is all reals such that x is less than or equal to 0. So you got to leave out one half of the graph or the other, so that you could do it like this, and then cut off the right side of the graph. Then you would be 1 to 1. Okay? So we have a similar problem when we look at the trig functions, which are clearly, let's try 150 zoom here, okay, which clearly are not, trig function goes on forever, right? Goes on forever. So here you have a failure, at many places you have a failure of the 1-to-1 test. However, if you look at this interval right here, this interval from negative pi over 2 to pi over 2, then the sine function is 1 to 1, and it passes the horizontal line test. You can see there's no place in this interval from negative pi over 2 to pi over 2, there's no place in this interval where the horizontal line, any horizontal line, intersects the graph more than once. Okay? So when we're talking about inverse functions, for trig functions, we have an interval. each trig function will have an interval. It's going to depend on what function it is. Okay, and it's from, in this case of the sine, it's negative pi over 2 to pi over 2. Now, let's just draw a quick picture here. Let me just throw in a unit circle here real quick. Okay, on top of my notes. All right. So when we're talking about, here's negative pi over 2, and here's pi over 2. So when we're talking about an inverse function, now what are we talking about with an inverse trig function? Okay. Well, what we're saying is you're going to put in a sine, and you're going to get out an angle. You're going to put in a sine, and you're going to get out an angle. Now, the sine, the output from the sine function, y equals the sine of x. Okay, you can have any angled input, right? All reals. The domain is all reals, right? You can have pi, 2 pi, 3 pi, a billion pi, negative pi. You can have negative a million, positive a million. Any of those, you can take any. All of those are possible angles, because the sine wave goes on forever. Positive and negative goes on forever in the positive direction and the negative direction. So here's the x-axis. So the domain is all reals for the sine function, but the range is y is less than or equal to 1 and greater than or equal to negative 1, right? You can't have a sine, or a cosine for that matter, that can be anything other than a number between 1 and negative 1. Now what that means is the range of the sine function is the domain for the arcsine function, right? Okay, so you can have, you're going to be, for the arcsine, you're going to be putting in a variety of numbers between 1 and negative 1, and the output will be an angle. But the output is only going to be an angle between negative pi over 2 and pi over 2. So even if the angle that produced the sine value, that was an angle that was a billion pi or whatever, the output from the arcsine, from the inverse sine function, is only going to be an angle between negative pi over 2 and pi over 2. Negative 90 degrees and positive 90 degrees, and nothing else. And that's because it is only here, it is only in this interval that it's 1 to 1. Okay? So the domain for the arcsine, or the inverse sine, it's called the same, they both mean the same thing, is the domain is negative 1, comma 1, okay? Here, I got these turned around. The range here is, and the domain is negative 1, comma 1. Okay? It's also called the sine. This is the arcsine, and this is called this is pronounced inverse. They mean the same thing, inverse sine. And this is symbolized by sin and then a superscript negative 1. The negative 1 standing for the inverse. Okay. So, to recap, the sine function has an inverse function called the arcsine or the inverse sine, in which you put in a sine value anywhere from between negative 1 to 1, and you get out an angle. But the angle output is only from negative pi over 2 to pi over 2. Okay, so let's play with this a little bit. Okay, so example 1. A, the arcsine, negative 1/2. Now, we don't know what angle produced this, but you see negative 1/2 for the sine, okay? And you got to know this isn't 60, this is 30. Look at all this. Okay, but it's negative 1/2. Let's look at this here. So the sine is negative 1/2. So we're looking at the interval between negative pi over 2 and pi over 2. where there's a negative sign. Now here's the interesting thing. In this interval, this right-hand hemisphere of the unit circle, or of a circle of values or whatever, because in this case it's not a unit, well, I guess it is a unit circle, but whatever. There's only one place where the sign can be negative, whereas on the entire unit circle, there's two places where the sign can be negative 1/2. It could be negative 1/2 right here, okay, which makes for ambiguity. And what that means is if the range of the arc sign was 0 to 2 pi, then the output, there would be two outputs. Two outputs. Actually, there'd be two outputs. All right? So, but we don't want that. Okay? We only want one output. So we're only going to consider outputs that are occurring in the right-hand hemisphere. Okay, so we look at negative 1. Well, here's negative 1/2. Okay, the y value of negative 1/2. This is the only place you can have a y value of negative 1/2 is right here. Okay. All right. So notice this is negative pi over 2, and this is where the sign is negative 1, and here is where the sign is 1, right? Okay, but here's where the sign is, right here is where the sign is negative 1/2, okay? Let's just think of this as angles encompassing, whatever. Okay, so we got negative 1/2. So you're going to know right away theta prime, the reference angle is 30 degrees, right? Okay, but the angle from here to here is negative 30 degrees, or negative pi over 6, right? Negative pi over 6, right off the unit circle. And just parenthetically, the cosine this is negative 1/2 y coordinate, and this is root 3 over 2 x coordinate. Okay? Now, when you're thinking about this, just a couple of things to think, there's two ways to approach this. You draw the unit circle, and you can also draw the sine function, the graph of the sine function from pi over 2 to negative pi over 2. Okay? And you can line, so where is it? Here is negative, right around here is negative 1/2. Okay, well, it's easy to see that's going to be around 30 degrees. Okay. Inverse sine of root 3 over 2. Okay. So, again, let's use a different, let's use orange. Okay? The right hemisphere, that's all we're considering. Okay? And let's draw ourselves the sine function, negative pi over 2, pi over 2. Okay, so here it is right here. Okay. All right. So, root 3 over 2. It's going to be up here somewhere. All right. So, we know that when the sine is root 3 over 2, here's theta prime right there. Theta prime equals 60 degrees, or pi over 3. And that's the angle that it is. This is the only possible angle in the right hemisphere that can have a sine of root 3 over 2. Now, in quadrant 2, there are angles that can have a sine of root 3 over 2, but we are not considering any output that can be in quadrant 2 or quadrant 3. And that's fine. Why? Because all the possible inputs are for the sine are found between negative pi over 2 and pi over 2. Okay. Or outputs, I mean. And the possible inputs go from negative 1 to 1. All right. So the inverse sine of root 3 over 2. Now, the inverse sine of 2. Now remember, the domain of the inverse sine, the domain, is x is less than or equal to 1 and greater than or equal to negative 1. Well, 2 doesn't fit in there. There's no sine value that's 2, so this does not exist. Okay. Page 322, number 5. Okay, let's do that. A, the arc sine of 1/2. That's the inverse sine of 1/2. Okay. Well, in the right-hand hemisphere, there's only one place, one angle that can have a sine of 1/2. That's 30 degrees. Okay, or pi over 6. The arc sine of 0 degrees, of 0. Well, where does the sine equal 0? Well, where does y equal 0? Right in the unit circle, right here at 0 degrees. Okay, now it also equals 0 at 2 pi, and it equals 0 at pi. Okay, but we don't care about those angles because the range for the arc sine is y is less than or equal to pi over 2 and greater than or equal to negative pi over 2. So the only angles we're considering are from pi over 2 to negative pi over 2. Nothing else. Okay? All right. Example 2, graphing the arc sine. Okay, now this is, all you're going to do is here is make tables. Okay? Y equals arc sine of x, or the sine of y equals x. Okay? If it's 1 to 1, then that's another definition for the inverse. It's equivalent for y equals negative pi over 2 comma pi over 2 in this interval. So y equals the arc sine of x. You can put in these numbers and then graph them. And you can see what you can do this for yourself, and you can see what the graph looks like. And then I did page 322, number 15. And they wanted you to make a table. You obviously have to use your calculator to do this. From negative 1 to 1 and progressing by 0.2. You plot all the values from negative 1 to 1. And so that's the x values. That's the inputs. Okay? That's the domain. Notice the ranges. Go from negative pi over 2 to pi over 2. Okay? And so here's the y values right here. All right. And then there's a picture of the graph. Okay. What's the y-intercept? 0, 0, x-intercept, 0, 0. Symmetry about the origin. Okay. Other inverser, that's cute. Other inverse trig functions. All right, the cosine. Now the cosine, notice how the cosine, where it's 1 to 1, okay? The cosine is 1 to 1 from 0 to pi. Okay, from 0, this is pi over 2, or 90 degrees. Okay, that's where the cosine is 0. Okay, so notice that here it goes from 1 to negative 1. Okay, so the arc cosine, the domain, just like the sine, has to be x is less than or equal to 1, greater than or equal to negative 1. But the range is y is less than or equal to pi, greater than or equal to 0 pi, or 0 degrees, or whatever. Or y is less than or equal to 180 degrees, and greater than or equal to 0 degrees. Okay, now here we go into a graph of the arc cosine, etc. We got the inverse tan. Now, the tangent, the arctan or the inverse tan, the domain is all reals. You can have, the tangent can go from negative infinity to positive infinity. The range is y is less than or equal to pi over 2 and greater than or equal to pi. So it's in this interval that the tangent is 1 to 1. But the tangent, so, and then you can use this to make the graph or whatever. All right, so let's, in page 318, example 3, we're evaluating inverse trig functions. So A, the arc cosine of the square root of 2 over 2. Now this is a number. Now notice the input. It is it's less than 1 and it's greater than or equal to negative 1. Now you should recognize right away that square root of 2 over 2 is a dead giveaway for pi over 4. Okay? Or 45 degrees. So, and here is the, here's the graph of the sine. So when it's pi over 2, when it's pi over 4, okay, right here. All right. Then this is square root of 2 over 2. So when the input is square root of 2 over 2, the output is pi over 4. Now, let's look at the unit circle. Now we're looking at from 0 to pi. Now, the cosine is positive in this in quadrant 1 and negative in quadrant 2. And it goes from 0, it goes from, the cosine goes from 1. When pi is 0, the cosine is 1. And when the angle is pi, the cosine is negative 1. And at pi over 2, the cosine is 0. Okay? So you can see that all the possible values, the input values for the arcsine, are encompassed, for the arc cosine, are encompassed by restricting the domain from 0 to pi. So the range is from 0 to pi. Okay, so 40. So there's only one angle that can have a cosine of 45 degrees. Okay, they can have a cosine of root 2 over 2, and that's 45 degrees. So only one angle, and that's pi over 4, 45 degrees. Okay, the inverse cosine of negative 1. All right. All right, so where was I? Okay, so the inverse cosine of negative 1. Now, again, let's draw ourselves a little circle here. And this is the unit circle, and we're only considering from 0 pi to pi, so right here. And, well, where is the cosine negative 1? Well, right here. Okay, right? This is, what are the coordinates here? Negative 1, comma 0 at pi degrees. So if the input is negative 1, then the output has to be pi or 90 degrees. Okay, now the arctan of 0. The arctan of 0. So let's think about where the tangent is going to be 0. Now, we're only considering the right-hand hemisphere for the tangent. tan, the other way to tackle this is the tan equals opposite over adjacent. It equals y over x. So when the tangent equals 0, when y equals 0. Okay? Now, in this right-hand hemisphere, where do you have an xy coordinate where y is 0? Well, at 0 degrees. Okay? Here, x is 1 and y is 0 at this point right here. Okay? So, clearly, at 0 degrees, the tangent is 0. Okay? And the inverse tan of -1. Okay? Well, let's draw another picture here. Now we know the tangent, when the tangent is 1, that's going to be, remember it's y over x, so y over x are the same. That's going to be a reference angle of 45 degrees. Now we're only considering the right-hand hemisphere. So here, reference angle of 45 degrees. Here, remember, it's square root of 2 over 2, comma, square root of 2 over 2. But these are both positive, and the tangent is positive. Where's the only place where the tangent is negative? Oh, the yellow, you can't see yellow, let's do blue. Is right here, where the coordinates are root 2 over 2, comma, negative root 2 over 2. So here, the tangent, the tan, equals -1 for negative pi over 4, or negative 45 degrees. Moving on. Okay, are we doing number 9? I guess we're doing number 9. 9a, arctan of root 3 over 3. Okay, now, this is one of the things you want to remember. Okay, the reference angle of 30 degrees has a tangent of root 3 over 3. So again, let's draw the unit circle. Here's a graph of the tangent. Okay, so here's the only place where you're going to have a tangent where 30 degrees, right here. Okay, this is the only place where the tangent's going to be positive and the reference angle is going to be 30 degrees. Okay, because we're only, see, I shouldn't have through the whole circle. We're only considering the right-hand hemisphere when we're talking about the tangent. Sine, it's the top hemisphere. I'm sorry, sine is the right-hand hemisphere, cosine is the top hemisphere. All right. Okay, and then for b, negative pi over 4. For -1, okay. This is the only place for negative pi over 4. This is square root of 2 over 2, comma, negative square root of 2 over 2. So here the tangent is, the input is -1. So the tangent is -1. This is the only place in the right-hand hemisphere where the tangent could be -1, these coordinates. So the output must be, and the only angle that you can consider is from negative pi over 2 to pi over 2. So the only angle it could be is negative 45 degrees, or negative pi over 4. Example 4, calculators. Let's just look at those real quick. Oops, that's not what I wanted to do. I wanted to hit the calculator. Okay, so we'll do second. Hit second and then tan, and that gives you the arctan. Notice it's symbolized with the inverse tan, whatever. Negative 8.45. Okay, and the output is negative, and etc. Okay, arc cosine, that's simply second cosine of 2. If you put in 2, you're going to get an error. Okay, it's outside the domain, right? Okay, very good. All right.
I'm gonna just buy some videos, okay? So I'm gonna.
Yeah, that's cool. So the inverse cosine of 0.75. Well, okay, you can do that yourself. All right, let's move on here. So, page 319, example 5, parent functions. So f of x equals the cosine of x. And then it can be shifted. So the arc cosine can be shifted into the arc cosine of x minus 2. And it's shifted 2 to the right. That's all. And it can be reflected. So here is this is the arc cosine of x. And this is the arc cosine of negative x. All right. Now, here's where it gets fun. Compositions of functions. Now, if you take if you compose if you take f of the inverse of x, then you get x. And if you take the inverse of f of x, then you get x back. Okay? So if you take the sine of the arcsine of x, you get x. And the arcsine of the sine of y equals y. Now, we're sticking to negative pi over 2 here. All right, 2 pi over 2. So let's look at example 6. What exactly does all this mean? Okay. So we're going to take the tan of the arctan of negative 5. Now, this looks really confusing. It's actually extremely simple. The first thing you're going to do is you're going to construct an xy axis, and you're going to restrict it to the hemisphere within which the tangent is 1 to 1. And that's quadrant 1 and quadrant 4, the right-hand hemisphere. And then simply construct the tangent in there. Okay, so in those two quadrants, and it can only be in one place in those two quadrants, because the tangent is positive. Remember, the tangent is y over x, or opposite over adjacent. So it's positive in quadrant 1, and it's negative in which y is negative and x is positive in quadrant 4. All right, so we have the tan equals negative. So we have opposite over adjacent equals negative 5 over 1. Okay? So this is negative 5, and this is 1. All right? So now what is the tangent of whatever angle? Now we don't know what angle this is. We haven't figured it out. We could, but we don't need to figure it out. All we know is that the tangent of that angle is going to be negative 5. Okay, so we're doing the tangent of the arctan of negative 5, and then so the output's going to be negative 5. Now this is not always going to be the case. Okay, so let's talk about when this isn't the case. All right. So in other words, we could have done the tangent. So let's talk about here. The arcsine. Now note, before we were doing the tangent of an arctangent, now we're doing an arcsine of a sine. Okay? So the input is the non-inverse function, the output's the inverse. So we're doing 5 pi over 3. Okay? Well, first let's draw 5 pi over 3. Here's 3/3. 4/3, and here's 5/3 pi right here. 5 pi over 3. All right. Now, note that not in range of arc sine, right? Remember, the range of the arc sine is y is less than or equal to pi over 2, greater than or equal to pi over 2. At least, whatever. Should have done it the other way. I could always mix it up when I do it that way. Y is less than or equal to pi over 2, greater than or equal to negative pi over 2. All right. So here's 5/3 pi right here. Okay. But we're only considering as output angles that are between pi over 2 and negative pi over 2. Therefore, we are going to take the coterminal angle that's with the same terminal side, okay, and that would be negative pi over 3, or negative 60 degrees. So we're not going to use 5/3 pi, or 300, this is 300 degrees. Instead, we're going to use as the output from the arc sine of the sine of 5 pi over 3. So notice the input is outside the range of the inverse. Okay? All right. Now, another way to think about this is the sine of 5 pi over 3 is negative square root of 3 over 2, right? So think of the arc sine of negative square root of 3 over 2. That can only be negative 60 degrees or negative pi over 3. It can't be anything else, because the range of the arc sine, as I've said a million, you're probably sick of hearing me saying it, is from negative pi over 2 to pi over 2, the right-hand hemisphere. Okay, now here's a trick question. The cosine of the inverse cosine of pi. Okay, well, now remember, the domain of the inverse cosine is x is less than or equal to negative 1, less than or equal to 1, and greater than or equal to negative 1. Now, pi is a number, 3.1, whatever, okay? It isn't between negative 1 and 1. They threw pi in there to mess with you, to fool you, okay? Don't be fooled. Okay. Page 323, number 55. Okay. The cosine of the arc cosine of negative 0.3. Now, negative 0.3 is okay as a domain for the arc cosine because it's between negative 1 and 1. So let's just draw. So here's 0 and here's pi. Okay. Now, this is x equals 1, x equals negative 1, x equals 0, right? Okay. And this is 0, and this is pi over 2, and this is pi. Okay. Well, where is, now this is, the cosine, this is negative 3 over 1. So this is the x coordinate. This is, remember, it's x over y or whatever. So here is where you'd have negative 0.3. It'd be right around here, okay? Because here's 0 and here's negative 1. So negative 0.3 would be right about here, okay? Now, this is adjacent over hypotenuse, or if you're on the unit circle, it's simply the x coordinate. You could think of it as x over y. All right? So, Now, we're not going to figure out what the y-coordinate is here because we don't really care. Okay? Why? Because we're doing a composition of functions. The question is negative 0.3 as an output from the cosine within the range of the arc cosine? Well, it most definitely is. It's right here. It's within the top hemisphere. So we can just simply say the cosine of the arc cosine of negative 0.3 is negative 0.3. Okay. Evaluating compositions of functions. The tan of the arc cosine of 2/3. All right, so let's construct the cosine. All right. Now, we're just going to take, here's 2. Remember, it's adjacent over hypotenuse, or x over y. Okay? So it's 2 over 3. Adjacent, here's theta, it's adjacent over hypotenuse. Okay? Now, why am I putting it over here? Well, we are only looking at cosines from 0 to pi. Okay? So this is the only place where the x-coordinate, or the cosine of theta, is going to be positive. It's going to be negative over here. It's positive in quadrant 4, but we're not looking at quadrant 4. Therefore, since I'm restricted to quadrant 1 or quadrant 2 for the cosine, I know that the y-coordinate is going to be square root of 5 just by using the Pythagorean theorem. So this is 2, this is 3. So this will be, the square root of 9 minus 4. It's the square root of 5. Okay, so what's the tangent of this angle? I don't even need to know what the angle is because I have the right triangle constructed here. It's going to be opposite over adjacent. Okay, or y over x coordinates. Okay, this point right here. Okay, and that's going to be root 5 over 2, and that's that. Okay. So that was example A, I guess, whatever. B, the cosine of the arcsine of negative 3/5. Okay, so what am I going to do? Well, the sine, the arcsine has got to be in here, right? From pi over 2. Remember, the range for the arcsine is from negative pi over 2 to pi over 2. Okay, so the output's got to be restricted. It's restricted to quadrant 1 or quadrant 4. So even though there's 2 different places where the sine can be negative 3/5, it can only be negative 3/5 in quadrant 4 here. If I'm restricted to quadrant 1 and quadrant 4, it has to be here. So here's theta. Here's the theta reference. Okay, so the y-coordinate is negative 3. The hypotenuse is 5. Remember, it's opposite over hypotenuse. Okay? And therefore, the cosine of this angle right here, with this right triangle constructed, must be 4 over 5. The cosine equals adjacent over hypotenuse. So it must be 4 over 5. So, page 323, number 67, the cosine of the arcsine of 24 over 25. Okay, the arcsine is limited to here. So even though there's 2 places, quadrant 2, the sine could be 24 over 25, but for the arcsine, it can only be here. Why? Because I'm restricted in my output to quadrant 1 or quadrant 4. And the only quadrant in which the sign is positive is 24 over 25. So I got to figure out what the angle is. Well, I don't even need to know the angle. Here's theta. This is a right triangle. Okay. This happens to be a what do you call it? A Pythagorean triple. You can do the math on it or whatever. Okay, here I did it right here. Okay. So here's the, remember again, the sine is opposite over hypotenuse. So I got 24 over 25. There we go. All right, so that means the adjacent, the cosine, is adjacent over hypotenuse. So the cosine has to be 7 over 25. And that's that. Okay. Example 8. The sine of the arc cosine of 3x. Okay. Now it gets a little more interesting. Okay. Think of u, the letter u, as the arc cosine of 3x. The cosine of u equals the cosine of the arc cosine of 3x. So the cosine of u equals 3x. 3x is less than or equal to 1, greater than or equal to negative 1. Okay. So what does that mean? So we're looking at the cosine of 3x. So just what we're going to stick with, adjacent over hypotenuse. So it's 3x over 1. So here's theta. Just construct a right triangle. Stick theta in there. Okay? And here's 3x. That's adjacent. And here's 1, and that's a hypotenuse. Which means that the opposite side has got to be the square root of 1 minus 3x squared, minus 9x squared. And obviously, x has got to be less than or equal to 1/3 and greater than or equal to 0, because if it's, or less than 1/3. No, that's okay. It can be 1/3. All right, so anyway. So the sine of this is going to be 1 minus the square root of 1 minus 9x squared over 1. Okay, so in other words, this is the answer right here to that. Okay. Opposite over hypotenuse, in this case the hypotenuse is 1. Okay. Now, the cotangent of the arc cosine of 3x. Okay, we're using the same triangle. All right, so it's the cotangent is adjacent over opposite, right? Okay, so it's going to be adjacent, which is 3x, adjacent to theta, over the square root of 1 minus 9x squared. Okay, page 324, number 73. The cotangent of the arctangent of x. Okay, so the cotangent of the arctangent of x. And the tangent, what the hell? What did I do here? I got something mixed up. Let me look at 73. I got two different things. Unless it's asking for both. Let's say 73. Cotangent of the arctangent of x. All right. I don't know why I got it. Okay, so x is less than negative infinity, positive infinity, whatever. Okay, now let's construct the tangent of x. All right, so we have the tan, the arctan of x over 1. So let's consider that. Okay, the tangent equals opposite over adjacent. So we construct a right triangle where the opposite is x and the adjacent is 1. Okay. And so here we have, and here's theta. This is a right triangle. Therefore, h, the hypotenuse, equals the square root of x squared plus 1. Okay? And the cotangent of this is simply going to be 1 over x. And that's it. Now, work on the homeworks, and if you have any questions about any of those, then send me email about them.